Hello everybody, video number 6, the different types of equilibriums. There are more than one major one for us, but there are different kinds. So we will be able to call them physical or chemical or what's the other one? Phase. That phase is physical. Solution equilibrium. In equilibrium, a combination of two reactions. There's a forward reaction and a reverse reaction. They're happening at the same time. These next two pieces are the pieces that are the central theme for the unit. Okay? Ready? The rates of the two reactions must be equal. It's the rates that are equal in the chemical equilibrium, okay? Of all equilibriums. So that one step forward, there's going to be one step back. Two step forwards, there's going to be two steps back. The rates of the reactions are equal. And because of this, the concentrations of the products and the reactants will be constant. So the rates are equal, the concentrations are constant. And I need you to ingrain that into your brain because students' biggest mistake is to try to tell me or, the New York State that the concentrations are equal. And the concentrations of reactants do not have to be the same as the concentrations of the products. I can have 2 moles of this plus 2 moles of this equals 1 mole of this other thing. Now their concentrations are not the same because 1 mole per liter is not the same as 4 moles per liter. Okay, so the concentrations don't have to be constant or equal. They have to be constant because if there's one step forward in the reaction, there's one step back, and it doesn't look like anything's happening. That's the key. There's something happening, but there doesn't look like there is because their concentrations aren't changing. The concentrations aren't changing, the colors don't change. Okay, concentration of H plus ions will give me to pH. pH changes, the color changes. The color won't change if the concentration doesn't change. Okay. Here's a pictogram, one little GIF about what is going on in a dynamic chemical equilibrium. So I have A plus B reacting to form AB. And then every time that happens, an AB breaks down to form A and B again. They're just diatomic. So you just need to take some kind of notes about what's going on here. One step forward, one step back. The rates of the forward reaction equals the rates of the reverse reaction. That's the key piece. Okay, and they're dynamic, they're robust. This is a different picture to show you what is going on where I have reactants, iron and CNS react to form a compound. The compound breaks down to form the elements, and there's a forward and a reverse reaction. Okay, the bottom is the reverse, the top is the forward. And so you just need to take some notes. If you want to draw that whole thing out, that's your business. If you want to write some words down that make sense to you about this, that is what I want. If you leave it blank, I'm not going to be satisfied. Okay, you've got to make some meaning of this picture. It's there for a reason. Okay, chemical and physical in solution equilibrium. So chemical equilibrium is that pictogram from before. So you need to write in here that the rate of the forward reaction equals the rate of the reverse reaction. A reaction at equilibrium will look like nothing's actually happening. The overall change in color here is never going to change because these things are actually happening at the same time. Every time the A and B form AB breaks down to A and B, and it doesn't look like there's ever any change going on. That's the truth. Okay. Physical equilibrium, this is phase equilibrium. So this is what happens before we actually change phase. So equilibrium will happen as I'm changing from gas to solid. This happened on the flats. So I would write down that this is what happens on the flats. But as one molecule of liquid goes into gas, another will go into liquid. And this is happening in a sealed container. So the initial state here, and this goes beyond phase change in this particular picture, by the way. There's the phase change physical equilibrium, and then there's this particular physical equilibrium where if I seal the soda, right, carbon dioxide is going to come up out and it's going to eventually stop, and the amount of carbon dioxide that goes back into solution is going to come back out of solution, right, and gas will go into liquid and liquid will go into gas. And actually that's a bad analogy, so let's just do water. Pure water will evaporate into gas, and then water will come into liquid, and water will change phase in there, and an equilibrium will be established. This will not be one of the big ones that we focus on. I just want you to know that it exists. Chemical equilibrium is what we're really interested in, okay? Solution equilibrium also happens when I get a saturated solution. So here's a solution that is saturated. I have all the ions dissolved in solution that I can, and there's powder remaining over. So now every time a crystal of the powder goes into the solution, some ions in solution must reform into crystal and come out. This is a solution equilibrium. These also happen. And this is very much like that physical equilibrium that we just did, except for now we're not talking about it going up into this other phase. We're talking about it happening within the liquid rather than a closed container, right, where the gas cannot escape. So when the gas cannot escape and can go back into liquid, we can get a phase equilibrium going on. Okay, so there are kind of equilibriums. Maintaining equilibriums, we generally have to have a closed system. And I've only seen this on some really old questions, but it is one of those things that is often overlooked but essential. Okay, so in order to have an equilibrium, the reaction must be reversible. I can't just go forward. If I go forward and I can't go back, there's no equilibrium. There's no backwards reaction. So first and foremost, to have an equilibrium, it must have a reversible reaction. Most times the system has to be closed because if I make a gas, the gas can't escape into the air, or that gas can't reform, even if it's chemical, can't reform back into whatever the products or reactants were. It can't form back into the different phase like liquid if it escapes. So generally systems are closed, and that's it. And we just did phase equilibriums just as a nutshell, like holistically, what is an equilibrium and what's going on. And now you got a little bit of understanding. So there we go. Press the button. If I could find it. If I could find a button.